So last time we figured out the maximum number of edges, right, in a triangle-free graph. Right, and the construction was fairly simple. You take, two sets of vertices. Each of them is basically half of the vertices, except when n is odd, you have to take floors and ceilings, right? And inside here, you put no edges. So inside of each class. And then between, you put, all possible edges, right? So this graph is, we mentioned this last time, but it's called the complete bipartite graph. So the notation is, k, n, floor of n over 2, comma, ceiling of n over 2. Like in general, KAB would be, you take a set of size A and a set of size B, and you put the edges between them. So today we're going to try to work out the extremal number of a clique, any clique, and the tight construction ends up being something similar. So more generally, if I have like K sub, S1, S2, up to S, K is the graph where I take sets of size S1, S2, S3, up to SK. So these things are numbers, right? Well, let's allow 0. So, right, I just take that many things in each part, and then I put no edges inside the classes and all the possible edges between the classes, right? So like, K2, 2, 3 would be like class of size 2, class of size 2, class of size 3, and okay, at some point I draw so many edges it doesn't, you can't even really tell if I've done them all, but yeah, something like that. Okay, so Turán's theorem, so this generalizes Mantle's theorem to any complete graph. So let's say that n is at least r, which is at least 3. So the graph, so I'm going to define this, I'm going to kind of state this a little bit of an implicit way, kind of like Kruskel-Katana. We're going to say what is the best construction, because it's quite annoying to try to actually count the number of edges in it. So I'll just say what is the best graph. So let me say the KR-free graph on n vertices with the maximum number of edges is the R minus 1, or the complete R minus 1 partite graph. And now I realize I should have said this terminology here. So this would be a complete k-part type graph if it has these kind of k-parts. Well, okay. I kind of feel like I don't want to have the parts having size 0 anymore, but let's not worry about that. Okay, the complete R-1 part type graph where all parts have cardinality or size, either the floor of n over R-1 or the ceiling of n over R-1. So if n was divisible by R-1, it'd be perfect, like every part would have the same size. Of course, not all numbers are divisible by all numbers. And then you've got to you've got to round it roughly. So as an example, like if if R was 4 and like n was 8 or something, then the best construction is going to be K2, 3, 3, right? So yeah, every part, basically you try to divide everything as evenly as possible, but you can't, so you just compromise, and some parts have size 2, some have size 3, right? So it's not hard to see that these graphs don't have a copy of KR, because kind of by pigeonhole, if I've got R-1 sets, if I chose R vertices, you'd have to have 2 in the same set by pigeonhole, but there's no edges in those sets, so that would not be a complete graph. Okay. Any questions about the statement? You know what's kind of nice about this kind of statement, this kind of implicit thing, is I don't actually have to give a lower bound construction, because I just say, oh, the lower bound, just take that graph. And then, yeah. So we just have to prove an upper bound. So yeah, like I said last time, there's lots of different proofs of Mantle's theorem. There's also lots of proofs of Turán's theorem. Again, this is one of those things, pretty much no matter, if you start in any reasonable direction, it will probably eventually lead to a proof. So let's do this totally differently than what we did for Mantle's theorem last time. But of course, this implies Mantle's theorem, right? In the case R equals 3. So this would also be a proof of Mantle's theorem. Okay, so what I'm going to do is I'm going to let G, well, just let G be the theoretical kind of best graph. So the n vertex KR free graph with the max number of edges. Okay, and then we're just going to, through just making a few observations, doing some combinatorial, things, we're going to determine that this graph just is that graph that I've described in the theorem. Which will also, by the way, show that the construction's unique, right? So as a byproduct of this approach, we're going to get that the best construction is actually unique. But let's worry about that at the end. So here's a claim. So if U and V are vertices of G, which are not adjacent, So UV is not an edge of G. Then I claim that they have to have the same degree. So to prove that, let's do it by contradiction. So let's suppose they don't. So this is now the proof of the claim. So if not, well, one of them has to be smaller. So let's say without loss of generality, the degree of U is smaller. So D of U is less than D of V. Kind of without loss of generality, we'll log. So basically, I mean, the only thing we know about this graph is that it's like KR free and has the most edges. So like, there's not much we can do. Essentially, the only thing you can really do is now just, I don't know, mess with the graph and get a graph with more edges that doesn't have a KR, and then it'll be a contradiction, right? And here's the idea. So I don't know, imagine you've got G. So U is here. Let's say it's got, I don't know, 3 neighbors. You know, it's degree 3 or something. And let's say V is degree 4. Their neighborhoods, they could intersect. I don't really know, but, you know. So one kind of natural idea, I want to increase the number of edges. The thing about, like, U is in some sense a little bit deficient. Like, it doesn't have very many edges touching it. So we would rather, like, have more vertices that look like, if I wanted to increase the number of edges, I want more vertices that look like V and fewer that look like U, if that makes any sense. I mean, we want the number of edges to go up. So yeah, all I'm going to do is I'm going to delete U, first of all, and then I'm going to sort of clone V. So I'll explain what I mean by that. But basically create a graph G prime as follows. So step 1, delete U. And when I delete U, kind of implicitly, like, you know, I've also got to delete all the edges that contain U. So whenever you delete a vertex from a graph, so we also delete, so and the edges containing U. Okay, so now this guy's gone, right? I've got one fewer vertex. I need to add another vertex. And what I'm going to do is just make another vertex V prime. So this guy's gone. And then I've got another vertex V prime. And I'm just going to make it adjacent to everything that V is adjacent to. So add a vertex V prime and edges, let's say V prime W for all W such that VW is an edge of the original graph. Okay. So, okay. What we have to do is we have to verify. So to get a contradiction, we need that this graph has more edges than G and it doesn't have a KR, right? The fact that the number of edges, it's kind of easy to compute. Although it does kind of require this, that U and V are not adjacent. So anyway, if I want to know how many edges there are, well, I've got the same number I had before minus the degree of U, right? Because I lost all these edges. And note that when I deleted U, it didn't change the degree of V because they're not adjacent. So when I added V prime, it added D of V edges. It would be slightly different if these were adjacent, right? But it would add D of V minus 1. And that's bigger than the number of edges in G, because d of u, v is bigger than d of u. And now to argue that it's KR free, well, think about the two steps. Can either of these steps introduce a KR? So the first step, I just delete a vertex. There's not going to be magically a complete graph on our vertices that appears by deleting a vertex, right? The second step, so after deleting this vertex, there's no KRs, and now I kind of clone the vertex v. So maybe let's talk about this as a sort of operation, right? Like we clone the vertex v, meaning you add a vertex with the same neighborhood. Well, if this new graph has a KR, then that KR must include the new vertex. But then I could just trade that vertex for this one, and it would still be a KR. Because it doesn't include both of these vertices. They're not adjacent to each other, right? So I could just trade that one for that one, and it would make a KR in the original graph, but that didn't exist. So G prime is KR free. So contradiction. Okay, so any questions about that one? So hopefully you can see so far there's no connection so far between this proof and the other one, right? We're not counting walks of length 2. Okay, second claim. So this one's kind of clever. I mean, it's a little bit less, takes a little bit more thinking than the other one. So there does not exist so distinct vertices u, v, and w in G such that UV is not an edge. VW is also not an edge, but UW is an edge. So the picture of the kind of forbidden structure, is so this dotted line means that there's no edge. So U is not adjacent to V, V is not adjacent to W, but U is adjacent to W. I guess probably I didn't need to say distinct. Maybe these have to be distinct anyway. But anyway, doesn't really matter. Okay, again, contradiction. Suppose they're, suppose they exist. So again, what we're going to do is try to find a way to delete a bunch of stuff from the graph, add a bunch of stuff, and end up with more edges than we had before without making a KR. And here, for this, actually, it's quite useful to have the first claim. Given that the first claim is true, we can actually say, U has the same degree as V, because they're not adjacent, right? That's by the first claim. But then there's a sort of transitivity thing going on. V also has the same degree as W. So they've all got the same degree. So by the first claim, they've all got the same degree. du equals dv, which is equal to dw. That's going to come in kind of handy. So we're going to kind of do the same thing as before. One nice thing is if I delete u and w, you can't delete the edge, this edge twice. And the edge is going to disappear the first time, and then that degree is now smaller because of deleting u, and it doesn't disappear the second time. So somehow deleting these two vertices decreases the degree by a sort of predictable amount, but it does deleting neither of these deletions affect the degree of v, because v is not adjacent to them. So somehow I can delete these vertices, lose a small number of edges, and then I could clone v, and I get a big number of edges because v's degree hasn't changed. So let g prime or g double prime be as follows. So you take g, we delete u and w, and then clone v twice. So again, clone is this thing, add a vertex with the same neighborhood. And again, we kind of already established that cloning something doesn't create KRs, right? Because, yeah, if I had one in the clone thing, it would contain that clone, but then I could just switch it to the other, the thing it's cloning, and that would be a KR as well. So yeah, G prime has no KRs, or G double prime. And now if I look at how many edges it has, well, start with the number of edges we started with, subtract the degree of u, subtract the degree of w minus 1, because once I've already deleted u, this edge is already gone. So the remaining number of edges I lose when deleting w is dw minus 1. And then I add the degree of v twice, because none of these deletions affected the degree of v. But all these degrees are the same, right? All these numbers are the same number. I'm subtracting it twice, adding it twice, and I've got this minus minus 1. So that's the number of edges in G plus 1, which is a contradiction. Any questions about that? Yeah, somehow it's quite useful to have established the first claim first, right? Because otherwise, maybe V just has a really small degree and this is useless, right? But they've all got the same degree. Okay, we're pretty much done. With this proof, anyway. So I want to say now that this graph just is a complete multipartite graph. And then we'll fiddle with like how big the sizes are, that they're all the same size and whatnot. But, you know, I claim that, yeah, G is a complete maybe, okay, yeah. I'll say it's an R-1 partite graph. And actually, maybe I don't regret letting the sizes have, the parts have size 0, because now let's say it's got R-1 parts. In theory, some of the parts could have size 0. I don't really, if there are fewer parts, just think of that as I've got parts of size 0. Okay, so to prove this, I mean, basically, we're just going to use this claim. Let's think about the complement of G. So we haven't talked about this yet, so I'll say that the complement of G is the graph G bar where it has the same vertex set as G, so V of G bar equals V of G, and the edge set is all the edges that are not in G. So the edge set of G bar, or the complement of G, is V of G choose 2, take away the edges of G. And generally the distance between two vertices in a graph is the length of the shortest walk. So we talked about walks last time. Between them, if it exists, right? Otherwise, we just say the distance equals infinity. So I claim that in the complement of G, there are no vertices that are at distance greater than 1, but not infinity. So in G complement, there are no vertices, like pairs of vertices, at distance, let's say L, where L is at least 2 and L is not infinity. Right? And the reason is, if there was, take a walk between them in the complement. And actually just take 2 steps of that walk. Well, and this is in G complement. If I take 2 steps of that walk, there's no edge in G complement here, because I could have just taken 1 step, right? So if I take 2 steps of that walk, what it looks like in G complement is this. But what it looks like in G is like this, right? Because to make G, I just flip all the edges. But that's like the forbidden substructure that we just dealt with in that claim. So let's say I take, the first 2 steps of the walk look like this. If such a pair existed, and then in G, it looks like this, but this is forbidden. By the second claim. So that's quite a restrictive condition on the complement. Any 2 vertices, either their distance is infinity or it's 1. So I think it's kind of clear at this point, G complement is just a bunch of cliques, right? If everything's at distance infinity or 1, G complement just looks like, a clique, so a blob with all the edges, a bunch of these cliques, right? And that literally is the same thing as G being a complete multipartite graph. And you couldn't have R non-empty parts, because that would make a KR if I just pick 1 vertex from every part. So the number of parts is at most R minus 1. So yeah, so G would be the complement of a disjoint union of cliques, which is just a complete multi-part graph. And yeah, you can't have R non-empty parts. Is that, that's good? Yeah. So now all we have to do is show that the parts are all pretty much the same size, but that's just a bit of counting. Well, not even counting. It's the same kind of thing as we've been doing, where you just, if the parts aren't almost the same size, I would just sort of delete something from one part and add something in the other part, and I'd increase the number of edges. So let's say A1 up to AR minus 1 be the, so when I say parts, I mean, the sets that are these kind of, these sets where all the edges are between the sets and none are in the sets. So G looks like A1, And yeah, if you had two of them that differed by, so if AI, the cardinality of AI and AJ differed by at least 2, or I should write this, let's write it like this. So if the size of AI is less than or equal to the size of AJ minus 2, what I would do is remove one vertex from the big one, so from AJ, and put it in AI. And so the number of edges, basically the number of edges lost So I think of it as deleting that vertex from AJ and cloning a vertex in AI. Number of edges lost is, so how many vertices did somebody in AJ have? It's adjacent to everything that's not in AJ. So it has degree n minus the size of AJ. And the number of edges gained well, you have to be a bit careful because so when I, and then there's all the rest of the graph. When I pluck out that vertex, I do indeed lose this many edges. When I add a new vertex here, it won't be adjacent to that thing I plucked out. So the number I gain is n minus 1 minus AI by adding a vertex there. But since the gap was at least 2 between these things, this is going to work out nicely. So, so in total, so the number of edges at the end is how many I had before minus n minus AJ plus n minus 1 minus AI. Yeah, which so number of edges minus 1 plus AJ minus AI, and AJ is at least 2 bigger than AI, so that's strictly greater than the number of edges in G. So all the parts have to have roughly the same size, they can differ by 1, right? So this is just saying the parts cannot differ by 2. Yeah, but yeah, they could differ by 1 because this doesn't work, right? If the parts differ by 1, I pluck one out of here and I add one to the other class. It's the same graph again, right? Any questions about any of this? Okay, so this is like a second proof of Mantel's theorem. Like, it's a proof of Turán's theorem. It gives a second proof of Mantel's theorem. We're going to prove something else later in the course, like a sort of something called a stability version of Turán's theorem, which will also imply Turán's theorem, and it'll be a totally, totally different argument. And also, actually, I think on your third assignment, you're asked to do another proof of Turán's theorem. Yeah, and there's lots more in the notes and stuff, or in the other exercises in the chapters. Maybe I wanted to just spend a few minutes here foreshadowing what we're going to do next time. So both of these theorems, they give a nice answer for complete graphs. Things become a little bit more complicated when you're dealing with a general graph. Well, I mean, on one hand, it becomes more complicated, but on another hand, it still has a fairly good answer, although you have to be open to like asymptotic, like just a sort of asymptotic answer. So like, I don't know. So for example, yeah, so what is the max number of in an H-free graph, this is basically what we're going to work out for most graphs H next time. For a general but it's not going to be such a perfect answer. So all we're going to be able to do is to say up to a 1 plus little o1 factor. Maybe I'll even state the theorem that we're going to prove. But yeah, just to kind of highlight how, probably you've heard of the Peterson graph, right? Or, 5-cycle, or, you could draw all kinds of crazy graphs, but no matter what the graph is, we're going to roughly figure out the answer to, what is the, so in other words, what is EX and H? It turns out it boils down to the chromatic number of the graph. So maybe I'll, so a proper coloring of a graph H is a labeling of the vertices, well, a labeling or a coloring of the vertices so that adjacent vertices get different colors or labels. Okay. And the chromatic number, so this might be familiar to some people. If it's not, probably it's not such a big deal. It's not too hard of a concept to grasp, I think. So the chromatic number of H, it's just the minimum number of colors in a proper coloring. So the notation here is chi of H. So chi of H is the chromatic number. So like for like a 5 cycle, the chromatic number is 3. If you standard kind of coloring with 3 colors would be like this. And you can't do it with 2 because it's not bipartite. It's got, yeah. Probably you've seen that theorem that, you know, something's bipartite if and only if it doesn't have an odd cycle. Yeah, so actually, like, there's a kind of natural construction for any graph of chromatic number R, let's say. Right, if I wanted to get a lower bound on the extremal number, I could just take a complete R minus 1 partite graph, just like we did before. So note, if the chromatic number of H is R, then a complete R minus 1 partite graph has no copies of H. The reason is, like, for the complete R minus 1 partite graph, I could color each part with a color. That's R minus 1 colors. And if there's a copy of H, that coloring would also color the copy of H with R minus 1 colors. So, you know, so it can't have a copy of H. So this, like, in particular implies that the extremal number of H is at least what we determined for the clique. So it's at least the extremal number of Kr if H has chromatic number R. Because, yeah, take the same construction we did before. It'd be really nice if this was just like equal or something. It's not. But it's sort of roughly equal. So what we're going to prove next time is this thing called the Erder-Stone theorem. Which says that for any graph H with at least one edge, otherwise it's kind of trivial anyway. I mean, we'll see why you need an edge, but with you know, at least one edge, basically you can't avoid copies of a graph that doesn't have edges. So, so the extremal number of H is like 1 plus little o1. We did talk about this asymptotic notation at some point. You might need to refresh yourself on that. So chromatic number of H minus 2 divided by chromatic number of H minus 1 times, let's say, n squared over 2. So to kind of try to convince you that this is sort of like the thing we got in Turán's theorem, like think about the case. Let's think about even the sort of Mantle theorem kind of case. Let's say the chromatic number is 3, right? What would I get here? I would get 1 plus little o 1, 3 minus 2, which is 1, over 3 minus 1, which is 2. So 1/2 times n squared over 2, which is like, n squared over 4. And remember, for the triangle, what we got was like n squared over 4 with the floor. So that kind of checks out for the triangle if you plug in the chromatic number. And if you plug in another, chromatic number equals r, you'll see that, yeah, roughly, I mean, the number of edges we're talking about here is asymptotically the same as what you get in Turán's theorem. Yeah. Because, if the chromatic number is 4, I get 2 over 3 n squared over 2. N squared over 2 is basically n choose 2, right? So, and if you think about it, this complete tripartite graph, if you think about it, it has about 2/3 of the total edges in it. The total number of edges possible would be n choose 2, which is like n squared over 2. This has about 2/3 of the edges, because if I pick 2 vertices at random, the chances they end up in the same class is 1/3, basically. So the chances they end up in different classes like 2/3. So this has about 2/3 of the edges, basically. And yeah, so I think this is probably going to take us more than one class. So we'll start proving this next time, and then we'll finish it next week, I guess.